90 meters below the surface of the North Sea, an underwater robotics arm locks a hydraulic torque tool onto a heavy subsea steel connector. This map of the North Sea, overlaid with recent data, shows a clear and pressing trend. Across these major, mature offshore fields, baseline oil production is dropping fast. Energy companies are still frequently finding small pockets of remaining crude, like the 10.4 million barrels recently identified at the Teal West field. But traditionally, these discoveries have been classified as stranded. They earn that label because the economics simply do not work. An operator cannot justify spending $1 billion and waiting 5 years to fabricate a massive, dedicated steel mega-platform just to tap a small, isolated reserve. So operators are caught in a bind. The market demands immediate new barrels to offset declining legacy wells, but traditional construction takes too long and costs too much to make those small reserves profitable. The offshore industry is left staring at an economic bottleneck. They have proven oil right under their feet, but zero financially viable way to build the standalone infrastructure required to pump it. The solution to this crisis bypasses new platform construction entirely. Instead of building new steel, operators are routing new oil into existing, older facilities. This diagram illustrates exactly how they do it. It is called a subsea tieback. Think of it as a massive underwater extension cord that connects a brand new, modern wellhead on the seafloor directly back to a legacy floating production vessel positioned miles away. Over a distance of 3.4 kilometers, engineers lay 2 distinct lines on the seabed. One pipe pulls the physical crude oil, and the other line, called the umbilical, carries the critical data and electrical power required to control the well. By plugging new wells directly into existing infrastructure, operators secure fast barrels, while instantly extending the commercial lifespan of aging vessels that were otherwise slated for decommissioning. To see how this physical connection works in practice, we can look at the recent Teal West project, executed by DeepOcean and Anasuria. The primary operational mandate for this specific connection was strict. The entire installation had to be executed without putting a single saturation diver in the water. Instead, operators piloted remotely operated vehicles, or ROVs, through the murky water. These robotic systems handled all the heavy subsea pipeline connections and umbilical terminations at a depth of 90 meters. The most delicate maneuver is the turret pull. The heavy, flexible production riser is winched straight up from the seabed, passing directly through the internal eye tube of the floating vessel's hull and into the topside machinery, all without human water entry. Because the heavy fabrication was skipped entirely, initial oil can begin flowing in a matter of weeks, proving the speed and capital efficiency of the subsea tieback. But while this diverless robotic execution is a massive physical success, bolting the heavy steel together underwater is actually the easiest part of the job. To understand the hidden danger of these projects, you have to look at the industry distinction between greenfield and brownfield engineering. Greenfield commissioning is safe and predictable. You are building and testing brand new systems on dead, unpressurized pipe in the dry, controlled environment of a shipyard. Brownfield commissioning involves integrating a new, high-pressure well into an aging facility that is fully live, highly pressurized, and currently producing thousands of barrels of oil through neighboring process trains. The Anasuria vessel is 30 years old. Any new connection is a high-risk surgical operation on a living, fragile mechanical system. Brownfield tiebacks represent the highest-risk commissioning scopes in marine energy because the threat shifts from physical leaks to digital logic errors. The ultimate challenge lies inside the control room. Engineers have to pull data from a modern 2026 subsea umbilical and feed it into a legacy 1990s vintage hardware environment. It creates a massive translation problem. Technicians must splice these modern digital communication protocols directly into the platform's original integrated control and safety system. This grid represents the emergency shutdown cause and effect matrix. It is the complex safety logic board that governs every valve, pump, and alarm on the entire vessel. The integration leaves no margin for error. If there is a single signal mismatch or a single false sensor trip comes up from the new well, the matrix logic will force a cascade, instantly closing every safety valve on the board. A single accidental trip shuts down the entire host platform. The revenue lost in just a few shut-in hours will exceed the total production value of the new well for its first month.
As the industry pivots to these tiebacks, leverage shifts to the integration engineers who can wire tomorrow's technology into yesterday's aging steel without shutting down the grid.